The optimization model implemented by Zara focuses on every article independently, but it considers all of the sizes in which this article is offered jointly. Its objective is to maximize the expected revenue derived from the sales of that article and across the entire store network. So its first term involves the sum across all stores of the expected sales for the upcoming week multiplied by the selling price for each store. The primary decision variables are the number of units of each size S to be shipped to each store J, which must obviously be an integer. The next constraint is a simple restriction which ensures that the total sum of shipments sent to all the stores do not exceed the available warehouse inventory. Because the model's objective involves expected sales, whereas the primary decisions are the shipment, a necessary component of the model is a function which specifies the relationship between the two and specifies it for every store. That function we've called the inventory to sales function. Its input variables include the vector of inventory levels of each size available in that store at the beginning of the week equal to the sum of the leftover inventory from the previous week plus the shipments. It also takes into account the demand forecast for that store, which are obtained from the previous forecasting step in the new process that Javier described earlier. The last constraint is a simple calculation of the inventory of each size left in the warehouse after the shipments are sent. This expression is used in a second term of the objective, which allows to control the total quantity of inventory sent to the network and ensures that the model's behavior is not myopically focused on the upcoming week only. This requires a user input we call the aggressiveness factor, which can be interpreted as the unit value of remaining inventory, so that this second term corresponds to the total value of the inventory left in the warehouse after the shipment. When this user input is high relative to the selling price, the model will tend to be more conservative when sending out inventory to the network, which could make sense at the beginning of an article's life cycle when only few sales data points have been observed and there's a high forecast uncertainty. In this case, one shouldn't commit too much inventory to faraway stores based on such forecast. Conversely, a low value relative to the selling price for that user input will push the model to aggressively ship out all remaining inventory. For example, at the end of the life cycle, when it may be desirable to free up some space in the warehouse. Let me now tell you more about this inventory to sales function, which I haven't specified yet. Remember that we need to relate the expected weekly sales in each store to the stock available at the beginning of the week in that store. Note that any graphical representation of that function must lie below the maximum value corresponding to the total forecasted demand for that store. Because sales can never exceed the inventory that's available, the plot of that function must also lie below this 45-degree angle line. The function we actually implemented can be represented qualitatively by the red curve, which has two important features. The first one is that beyond a certain shipment quantity, the marginal probability of selling additional units to that store decreases. This is called the saturation effect. This feature ensures that the model does not load up any given store with units which would have had a higher probability of selling in another store with less inventory, and overall tends to balance the model's allocation of inventory across stores. The second feature reflects that when there's only very few units of inventory left in the warehouse, they tend to not even sell at all because customers may not even notice them or they may not be displayed on the floor. This is called the exposure effect, and effectively pushes the model to progressively restrict the set of stores receiving inventory when there's not enough left for the entire network. That way, this inventory will not be spread out in many stores where it will sell nowhere because the exposure threshold may not be met in any of them. At Zara, this exposure effect does not only stem from the self-advertising function of inventory, but also is due to custom inventory display policies in the stores, which I'm going to describe now. In Zara stores, the display of each article is dynamically affected by the availability of so-called major sizes, such as medium or large. In this example of an article offered in 4 sizes, you can see that as long as there's some units of the medium or the large that are left in the store, the article will remain in the display area. However, when either the medium size or the large size runs out, a store associate typically moves all of the remaining units of the other sizes to the store backroom when the article will no longer generate sales, at least until the next store replenishment. This is only a simple example with 4 sizes, but this type of policy more generally applies to most of the articles that are sold by Zara. The rationale for that policy is to basically strike a balance between generating sales on one hand and on the other hand mitigating the frustration of customers who cannot find their size after they've identified an article that they would really like to buy in the store. From a distribution standpoint, this policy is extremely important. For example, if an article has been removed from display in a store because its medium size was missing, only sending back the following week units of, say, the small or the extra small will be completely useless from a sales standpoint, because in that case, the entire article will likely not even be brought back to the display area the following week. As a result of this, our inventory to sales function had to properly capture this policy and the dependencies between sizes that it introduces. For this purpose, we've developed a stochastic model taking as input the inventory of each size available in the store at the beginning of the week, assuming that the customer demand for each individual size arrive according to individual independent Poisson processes whose arrival rates are given by the available forecast. A key observation for the analysis is that the sales process for each size is interrupted every week, either when that specific size runs out, when the first major size runs out, in which case the entire article is removed from display, in that case the major sizes are medium and large, or by the end of the week, whichever comes first among those 3 events. This led us to study the random stopping times associated with these events, such as here the time when a size runs out, defined as the first instant when the cumulative counting measure associated with the demand process for that size equals the inventory initially available. Likewise, the first major size stocks out, the stock out time can be defined as the minimum of the previous size stock out time across all of the major size, again, in this case, medium and large. The expected sales for the entire article can then be calculated as the sum across all of the sizes of the cumulative demand counting measure for each size evaluated at the minimum of the 3 stopping times I just defined. By using a deep result from stochastic analysis called the Doob optional stopping theorem, we can then express these expected sales in closed form as a function of the demand forecast and the inventory available. Finally, we use a linear approximation in order to embed this inventory to sales function for each store into a mixed integer programming formulation for the entire network. And I'm going to show you that formulation now. For lack of time, I cannot explain all of these mathematical expressions, but for more details, you can refer to our paper due to appear in operations research. You can see here, however, that the structure of that formulation is rigorously identical to what I've shown you earlier, with the first set of constraints implementing the approximation of the linear inventory to sales function for each store, which I described in the previous slide. I want to emphasize that even though our optimization model ultimately comes down to an MIP formulation, the underlying problem that we're able to solve with that formulation is not deterministic, but rather stochastic. Ultimately, our model is able to trade off the shipments to different stores of limited inventory of all of the sizes in a way that capture the actual merchandise display policy in each store. For a couple of years now, Zara has been solving every week about 15,000 instances of this exact formulation. The next part of our presentation is a video which explains how these mathematical optimization and forecasting models were implemented and how they fit within Zara's entire distribution process from start to finish. As you watch this video, I suggest that you try to follow the blue jacket.
The distribution process begins at the store level, which is the visible face of the company, and is where there is the best understanding of what customers are demanding, From a distribution standpoint, there are two key pieces of information that are gathered at each Zara store. The first piece of information is the point of sales data that is captured daily and is transmitted directly to Zara's logistics center in Spain. The second piece of information is the bi-weekly order placed by each store. On the day they have to place an order, the product assortment for the next shipment is downloaded into a handheld device.
2 veces por semana hacemos el pedido de la tienda a la central, incluyendo los artículos por los que apostamos después de escuchar a nuestros clientes, y completamos los artículos destallados.
A very important aspect has to do with the availability of sizes. Most stores will only display merchandise for sale when the set of available sizes is complete enough. This is meant to achieve a balance between keeping inventory displayed to generate sales and mitigating the impact of missing sizes on brand perception. Therefore, if at any point in time a store associate realizes that the major sizes of a given article are missing, then it is likely that all remaining inventory of that article will be moved from the display area to the back room, especially if the same space can be used to display another product that is available in most major sizes. This way, the incomplete article is effectively removed from customers' sight. When preparing the bi-weekly order, the store manager will go through all the articles in the store and will also check in the back room for products that were removed from the shop floor because they were missing some of the major sizes. Zara has a fixed schedule of when the orders must be placed. The store manager is responsible for transmitting the information electronically by the cut-off time. The ordering process is repeated twice a week at each one of Zara's 1,500 stores for several hundred different products. The point of sales data and the orders from the entire worldwide network arrive at Zara's headquarters in A Coruña, Spain. The information is centralized and stored in the legacy database that is managed by Zara's systems area. Overnight, a subroutine automatically computes the sales forecast for each article at each store. The forecast is based on a regression model, and at a high level, its structural form is a weighted linear combination of the two key pieces of information gathered at the store level. That is, on the one hand, the objective and centralized time series data of historical sales, and on the other hand, the subjective and decentralized shipment request, converted into a sales prediction by taking into account store inventory. Once the forecast has been computed, the distribution team comes into play. This team consists of approximately 60 employees. Their responsibility is to determine the exact number of units of each size of each article that should be included in each shipment to each store. Therefore, they are the main users of the inventory allocation model. Each employee has access to the central database through a client application especially developed for this project.
Para cada artículo, el modelo recupera la estimación de la demanda y el stock de las tiendas y del almacén. El usuario puede modificar los parámetros disponibles haciendo un clic y el modelo optimiza la distribución del stock.
El modelo corre en un servidor dedicado para cada centro de distribución. Está codificado en AMPL y se resuelve usando CEPLES. Cada caso se resuelve en escasos segundos porque disponemos de muy poco tiempo desde que la información está en el sistema. Y en una semana normal aproximadamente podemos resolver unos 15.000 casos para distribuir 6 millones de prendas valoradas en más de 120 millones de euros.
The user at the warehouse can visualize the solution of the model through the client application. The interface allows the user to request additional runs of the model in order to perform what-if scenario analysis. For instance, depending on the time remaining to the end of the season, the user might modify the aggressiveness factor to push more inventory to the stores.
Si fuera necesario, los usuarios pueden hacer cambios en el modelo. Estos cambios los solemos hacer cuando nos afectan factores que no captura el modelo, ya sean festividades, ya sean cambios climáticos, cualquier tipo de cambios que nos pueda afectar a la distribución en general.
The chosen solution is finally transmitted to the existing warehouse control systems, which effectively implement the physical picking, sorting, packing and freight loading operations. The warehouse is divided into two distribution areas, one for the hanging clothes and one for the folded clothes. In either case, the first step to implement the model's output is picking the items in the solution. This is done in a wave picking fashion, in which the same article is picked at once for all the different stores in the next shipment. The second step is sorting, so that different items going to the same store are put together in the same shipment. For the hanging clothes, there is a dedicated rail for each store, and for the folded garments, a state-of-the-art sorter is used to place each item in the right shipment. Barcodes are used to identify the type and destination of each item and to tell the sorter in which box to drop it. Shipments are made by truck or by plane for more remote locations, so that the items reach the destination store within 48 to 72 hours. In the case of ground transportation, the trucks are loaded directly at the docks attached to the warehouse. In the case of stores that are reached by plane, an air cargo container is filled at the warehouse, which is then transported to the airport and loaded onto the aircraft. The shipment finally arrives at the store where the items are unloaded. The store associates check the products and quantities that arrived, which might be different from what they originally ordered, depending on the optimization performed by the model. Most of the items will be placed immediately on display. With the new shipment, the store associates can now complete the set of sizes of an article that was moved to the back room before the previous order, and the entire article can be brought back to the display area. Indeed, the model allows to send only the missing units in a size profile, so it constitutes a good display. Once it is back on display, the article can effectively generate sales without affecting customer perception due to missing sizes.
As you can see, the blue jacket ended up in very good hands. I will now leave the floor to Felipe Caro from UCLA for discussion of the impact of this work.
The development of the optimization model that Jeremy described before and its associated software took about a year. By the end of the summer of 2006, a prototype was fully operational, and in the fall-winter season of that year, we performed a live pilot experiment of the new process. This had been planned early on as a critical project requirement and was designed with 3 goals in mind. First, to provide a convincing proof of feasibility for the new OR-based process. 2, to help identify and act upon improvement opportunities for the new process before its full-scale deployment. And 3, to support a quantitative assessment of impact. For the pilot, 10 articles of the women's section were selected by a senior Zara manager as a test bed for the new process. These articles were selected with the goal of constructing a representative sample of Zara's assortment. Each test article was then matched with a control article, and the idea was to pair articles that were as similar as possible. Therefore, we matched them based on their type, the life cycle, and their sales performance prior to the beginning of the season, of the pilot, sorry. Our experimental design leveraged the fact that Zara had only 2 major warehouses, one in Arteixo, in the northwest of Spain, next to La Coruña, shipping directly to roughly 1/2 of the stores that Zara has worldwide, and the second in Zaragoza, halfway between Barcelona and Madrid, shipping directly to the remaining stores. Both warehouses ship exactly the same articles, but just to different locations. The new inventory allocation process was only implemented in Arteixo at some point during the life cycle of the 10 test articles mentioned before, while the legacy process was still used to distribute the control articles. In Zaragoza, both test and control articles were distributed using the legacy process. Specifically, in Arteixo, for each pair of articles, shipments were determined by the legacy process during the first part of the life cycle. After a sufficient number of weeks, we measured several key metrics, including sales, time on display, returns, and transshipments. Capital M in this slide denotes any of these metrics. Then, the distribution of the test articles was switched to the new process, while the legacy process was still used for the control articles. Towards the end of the life cycle, we measured again the same key metrics. We followed the same steps simultaneously in Zaragoza, except that the legacy process was used throughout the entire life cycle for both the test and the control articles. Once the pilot was over, to estimate the impact on each metric, we used a well-established and accepted methodology in event studies called difference and differences, which I describe next. In order to remove the effect of any initial conditions, we took first differences between the measurements made before and after the new process had been introduced. Then, we compared the performance of the test versus the control group by taking the difference of the matched pairs. This removed the effect of anything that could have happened during the pilot but was not due to the model, and in terms of our experimental design, it constituted a first dimension of control. In Arteixo, the average of these differences across the matched pairs represented the impact of the new process. By contrast, in Zaragoza, since both test and control groups were distributed using the legacy process, any difference can only be attributed to estimation error. The latter constituted a second dimension of control in our experimental design. As mentioned before, we measured several metrics, but first I will focus on sales, which is the most relevant metric from a financial standpoint. To ensure that the measurements obtained from the experiment were truly reliable, we first looked at the warehouse in Arteixo where the new process had not been implemented. We observed that the sales difference for each matched pair, which corresponds to a pink point in the figure, varied across the articles considered. This was to be expected because of the noise introduced by the matching process, the matching procedure, and the forecasting accuracy. However, what truly mattered to us was that the average difference was almost negligible, as it only reached 0.7%, which can be seen in the graph since the pink points are centered